there was one point in which fish occurred 7 times within a 24-hour period. And so you can ask, if you take a period of time, say 6 months, is that surprising? Did a miracle occur, or is it kind of common? Now, I like that problem for various reasons. One is that it's a well-posed mathematics problem. It's a clear story. Okay. The second thing is I can solve it. The third thing is it's hard enough that it's worth telling you. It's a little complicated because the windows intersect each other. When you do the math, the answer is the chance of 6 or more events in a 24-hour period over 6 months is about 22%. It's not a miracle. It's not surprising at all. The really surprising thing is, why was Jung surprised? What Fred Mosteller, my co-author, and I did was to go through each of Jung's stories and take them apart, do a simple back-of-the-envelope calculation, and say, you know, this isn't so surprising. And there wasn't one that survived. Okay. The next thing I want to tell you about is the most basic tool that I use. So when Fred and I first started working on this, we got on the front page of the New York Times as professors study coincidences. Well, the one thing I learned is if you get on the front page of the New York Times, you get a lot of funny letters. So we would have people saying, you know, what about this, etc. So when that happens, what do I do? Well, the image, the tool I use, it's called the birthday problem, and I'm going to start in the simplest way, but I'll build it up to something. Bear with me, but let's start with the simplest one. Suppose I have a group of people, and I ask the 2 of them have the same birthday. Well, most people, even I viscerally, find it surprising to find out that with a group of 23 people, like these 23 people, you're about 23 people here, 2 of you have the same birthday. It's pretty likely that 2 of you have the same birthday. That's a little surprising. And when you ask people about it, you know, how many people do you think you should have in a group to have even chances that 2 people have the same birthday? They say, well, birthday, that's 1 in 365. And, you know, so maybe half of 365, 183. And, well, that's what people think, and it's not quite right. Some people think that the question I'm answering or discussing is what's called the birth mate problem. That is, how many people do I have to talk to meet somebody who has my birthday? And that answer is, again, a little surprising. It's 253. It's more than half of 365. Why is that? That's because, imagine the people all lined up, and I'm asking them one at a time. Among all of those people, there are a lot of those that have matching birthdays, so you don't get the full list of them. And anyway, it's a lot more. But that's not the question. The question is, anybody could have the same birthday. So I could have the same birthday as Bama, or Bama could have the same birthday as Ingrid, or I know each of your names, watch out. Any pair of people could have the same birthday, and if you take the number of pairs, 23 choose 2, the number of pairs of people, that is about 253, and so it makes perfect sense if you think about it. So that's the vanilla-flavored birthday problem. And the thing is, to take away from that is, we're surprised even though the math says we shouldn't be surprised. Okay. I want to take that and make a tool out of it, and so what I'm going to do is head in that direction. So the first thing I'm going to do is change the number of categories. The birthday problem is a problem with 365 categories. A lot of people still have watches, old-fashioned watches that have second hands on them. I believe that second hands are random, and so you could ask, they're equally likely to be on each of the 60 seconds. You can ask, how many people do I need to have in a group to have even odds that if I say, now look, that their second hands are on the same second, that would be a birthday problem with 60 categories. Yeah. The math that goes behind the birthday problem says this: if you have a birthday problem with C categories, the number of people that you need to have in a group to have chance 50-50 that two of them match in one of those categories is 1.2 times the square root of C. So let's try it out. In the ordinary birthday problem, that's C is 365, and 1.2 times the square root of 365 is almost 23, so we round it up. Okay, so let me give you an example of how that's used. I was at a party, and a friend of mine, the psychologist Barbara Tversky, came in, and she was all excited, and she said, all right, you guys, listen to this. I just saw the new James Bond movie, and the 4 digits on the bomb, they matched the 4 digits on my Israeli bank account. What are the odds of that, Mr. Wise Guy? Well, I think 4 digits, that's anything from, 0000 to 9999. It's 10,000 possibilities. It's a birthday problem with 10,000 categories. How many 4-digit numbers do you need to keep track of in order to have a good chance that two of them match? Well, 1.2 times the square root of 10,000 is 120. It's not that big. And the 4 digits of your phone number, your friend's phone numbers, there are a lot of 4-digit numbers that we come into contact with. It really isn't surprising at all. Anyway, that's an example of how to use your thinking about the birthday problem. Here are other variations, which as I said, I'm trying to build a tool. Let me do this one. So, how many people do you need to have in a group to have even odds that two of them have a birthday within a day of each other? Okay, within a day of each other. Not so easy to think about, but the answer is less. It's less of a coincidence, and it's down to 14. And if you say within a week, it's 7. So around the dinner table, if you look, it's even odds that there are 7 people at dinner, that 2 of them have a birthday within a week of each other. Okay, so to take from that if you make what you count as a coincidence wider, it's easier to match, and it changes in ways that are hard to think about. This one's important enough that I'll try to show it to you. Suppose you're riding on a plane and you start talking to the person next to you, and you want to try to find, as we do as humans, something where we have something in common. So you might say, what's your father's name? Or, gee, I just heard a talk about the birthday problem. What's your birthday? Or, people talk about all kinds of things. And so there are many categories now that you could have a match in. And so I'm going to suppose that in your conversation, there are K categories. I made 3 here. Your birthday, the lottery number, or first name, last name. And so if you were just doing the birthday problem, that's 365. For certain lottery numbers, it's 1 out of 1,000. And for first names, I took popular first names to be 500. You could change that if you don't like it. So if you ask how many people do you need to talk to have even odds of a birthday match, we know it's 23. For a lottery match, 1 in 1,000, it's about 38. And for names, it's 27. But if you say, well, I'm going to count as a success a match in either the birthday or the lottery, then it's down to 20. And if you count as a success any of the 3, it's down to 16. So again, allowing more possibilities to count as something that surprises you makes it easier to be surprised. The answer in general, I put up because it's that nice version of the harmonic mean. But that's the number of people that you need if you have K sets of categories to have even chance of having a birthday match. 2 more versions, and then I'll stop. Multiple matches. This one's harder to think about, but let me ask the question. So we know that with 23 people, it's even odds that we have a match. How many people do we need to have in a group to have even odds of a match if we want 3 people to have the same birthday? Not so easy to think about. What about how many people in this audience? you know, have, you know, are there 10 people in this room that have the same birthday? Might be. So let me show you some numbers. Again, the math is doable. It's interesting math to do. These are the answers. So K is the number of matching birthdays I want to have. So if K is 2, that was the problem I've been thinking about. And N is the number of people you need to have in the group in order to have even chances of having K people with the same birthday. And so with a double match, it's 23. For a triple match, you need 88 people. You know, for 10 people, you need about 1,000. I don't think that there are 1,000 of us here, so probably there aren't 10 of us with the same birthday. But those calculations are interesting to do, and they're very hard to have any intuition about. Let me show you the general version of that, and this is the worst thing in my talk, so it's all back uphill from here. Okay, what's that formula? That formula is how many people N do I need to have in a group? If I have C people in my category, so 365 for the birthday, 1,000 for lotteries, I want a K-fold match, and I want the probability to be 1 minus P. I want the chance to be, I might not want it to be 50-50, I might want it to be 95% sure that it works. And the answer is this charmer. Okay, it's a good approximation. So let me give you an example of how that works. A friend, Laurie Beckett, came in one day and said, you know, I noticed that my birthday, my husband's birthday, and my daughter's birthday are all on the same day of the month. What are the odds of that, Mr. Weisberg? Okay, well, okay, it's a triple match. Same day of the month, there are 30 days in the month. So C is 30, K is 3. Plug into the formula, it's 18. So if you know the day of the month that 18 people were born on, it's even odds that you'll find 3 of them born on the same day of the month. So I hope you get the feeling that we could build the birthday problem up as a tool. Let me cut to the end of this and back to philosophy or something like that. So my definition of coincidence, at least roughly, was I had some events which seemed surprising and unusually close together in some essential aspects, and yet there was nothing causing that, no apparent causal link. So an abstract version of this, which I can't make mathematical sense out of, I wish I could, but meanwhile it makes sense to me and probably makes sense to you. Suppose there was something called perceptual space. Well, that's a big suppose, but suppose there was something called perceptual space, okay? And events come in and they sprinkle themselves in your perceptual space over time. And you can ask how close are points likely to be in our perceptual space if they're sprinkled in some random sense. And we have versions of the birthday problem that are general enough to handle, you know, random points in metric spaces and that sort of thing. And I won't say more about it. But the birthday problem is a powerful tool. Okay, that's enough of that. So the next thing I want to tell you about is mathematics meets the real world. And those of us who do applied mathematics are very aware that it's its own cup of tea. And this story that I'm about to tell you happened when I was a graduate student at Harvard, so it's a while ago. And my advisor, Fred Mosteller, got a call from the psychology department at Harvard, and they were investigating a young psychic who was supposed to have unusual abilities, and they wondered if Fred would come and take a look and see what they thought of this psychic's performances. Well, Fred's a famous old guy, and one thing he knows about is you don't go yourself, you send the kid. Okay, so he said, how would you like to go to the psychology department and see a psychic? Oh, sure. Okay. So I have to, you know, try to bring you along. So the psychology department is in William James Hall, which is this giant edifice in the Harvard campus, tallest building by far on the campus. And they were in the conference room, which was on the 12th floor. And when you're riding up in the elevator, these are some of the smartest humans that there are. And you think, gee, I wonder if there's something to it. Maybe my whole worldview will change. And you also wonder whether when you get there, you're going to see some guy lying on a tiger skin rug telling you about his deja vus or something like that. I was relieved to find the whole big room was covered with decks of cards. The psychic in question was not introduced by name, but he was called BD, the initials BD. And he was introduced as being a dropout from the Yale Law School, and he did unusual things. And so there were about 30 faculty and graduate students and BD and me watching. And what kinds of things did BD do? So here's a typical thing he did. He'd say, I want to do something, I need 2 decks of cards. Here's a red deck, would you shuffle that deck? And here's a blue deck, would you shuffle that deck? So the cards were shuffled up. And he said, you know, I want 2 cards named, any 2 cards, you name a card, you name a card. And somebody said 6 of hearts, ace of spades. Okay, good. Put the decks on the table. He was way away from the cards. Put the decks on the table. So there's a red deck and a blue deck, 6 of hearts, ace of spades. And let's start turning the cards over until one of those cards comes up. So people start turning the cards up one at a time. And the 6 of hearts came up. And he said, 14. And they dealt down 14 cards in the second deck. And there was the ace of spades. And it was quite surprising because he hadn't touched the cards and they were shuffled and other people named them, and you know, it was surprising. What I want to do is make you see that performance through my eyes, okay? So the first thing to say is he didn't say what he was going to do before the trick started, before the performance started, right? He had 2 cards named, okay. Now it might have been that when the top 2 cards were turned over, they might have been both ace of spades. Great, stop, you know, miracle, right? But they might have both been 6 of hearts, or 6 of hearts, ace of spades, or ace of spades, 6 of hearts. That didn't happen. So he said, you know, go down until you, so when the 6 of hearts came up here, it might have been that the other 6 of hearts was here, or that might have been the ace of spades, or it could have been the other way. Those are all things that would have counted and been equally as surprising. That didn't happen, okay? Then he said 14. He didn't say before he started, I'm going to say 14. He said 14, okay? They counted down 14 cards, and there it could have either been the matching 6 of hearts or the other ace of spades. And suppose that hadn't happened, you know, 13, 14, nothing. Turn over the next card. Now that also, you know, 14, turn over the next card, that's fine. If you just take those as possible outcomes, any one of those outcomes would have been just as surprising as what actually happened. The chance of that trick working are about 1 in 7. Okay? So it's not so surprising as the first thing, not as surprising as you initially think. The second thing that's interesting is his stuff worked about 1 in 7. Now, you might think, gee, that stinks, 1 in 7, but that helped everybody. They said, you know, if he was any kind of a magician, his stuff would always work. It doesn't always work. Something there, something strange there. So there was a lot of stuff like that. And then I have to report one other example out of many. But I'm watching him like a hawk, and I see him take the deck, here's the deck of cards, and look at the bottom card like a kid doing a card trick, you know. And it was the 3 of spades. 3 of spades. And he got all excited, and I said, I think something good is going to happen this time. And so did I. Okay. He cuts the cards like this, and he leaves a step. It's more than an inch. He's not a clever sleight of hand guy. So there's the 3 of spades. Okay. Then he spreads the cards out on the table, and he said, you know, somebody pull out a card. I don't want to touch anything. Pull out any card you like. And somebody pulls out a card from near the middle, and I see him count from the card that was pulled out to where the 3 of spades is, you know, with 5 cards in between them, okay? And then he backs away from the deck, and he says, push that card back in. I don't want to touch them. And he said, you cut the cards, cut them again. And he got the cards way to the back of the room, as if they were 1,000,000 miles away from him. And he said, so you're thinking of a card. He isn't thinking of a card. He pulled one out of the deck. Okay, you're thinking of a card. And he said, we need another card. Oh, say the 3 of spades. And he names the card he originally saw on the bottom. And then he said, we need a small number. And somebody said 2. And he said, we need another small number. And so he finally got 5. And then he had people, he said, what was the name of the card you thought of? What was the name of the other thought of card? Whatever it was, 3 of spades. Deal the cards down until one of those cards up. What was the thought of number 5? Count 5 more cards. There's the other card. So that particular thing was definitely sleight of hand and a standard kind of little magic trick. So now there were 2 hours of stuff like that. Now, why am I telling you about that? Well, let me explain that. Riding down in the elevator at the end of this, I was listening to people talking, and some people said, sometimes he touched the cards and I didn't like it. And other people said, yeah, but there were all of those times when the cards were 1,000,000 miles away from him. So that's a principle of deception of good magic tricks. That is, often magic tricks will have several different methods that they work. And the strong points of one method will offset the weak points of another method. And so somehow this is this, well, I call it the bundle of sticks image, but people somehow, we all do it, think a lot of bad arguments add up to one good argument. Well, okay. You might ask, well, was anybody fooled by that or convinced? Well, Science magazine, our premier scientific publication, announced 2 weeks later that Harvard University had given a grant of $20,000 to BD to explore the nature of his own psychic phenomena. So somebody was convinced. I went back to Fred Mosteller and he said, what do you think? And I said, the kid does card tricks. So he must have told that to some of the psychology faculty, because I met a guy as a friend, Bob Rosenthal, a very distinguished social psychologist, and he said, so I understand you think our boy does card tricks. And I said, wait a second, I don't think he does card tricks. He does card tricks. Okay, there's 2 different things. And he looked me in the eye, and I can't say this with the same conviction that he said it, but he said, nobody ever said he didn't do card tricks. We just think he has psychic ability. Okay, now that's a tough one. That's a tough one. Maybe my being in the room, my bad vibes, anything's possible. The story of BD goes on. I won't take you through it, but BD became a judge in North Dakota. I'm not making that up. And about 7 years ago, I got a call from the psychology department at University of Chicago. They wanted to do an investigation of a middle-aged psychic, and it turned out to be the same guy. And somebody said they should talk to me, and I think I made that go away. But so that's what actually happens when you're there, okay? But before coming to Harvard, BD had been down at Durham, North Carolina, at Rhine's laboratory, which isn't officially associated with Duke, but anyway, which was the premier parapsychology laboratory in the world, maybe. And there had been 3 articles in their journal about this unusual psychic. And if you read them, they report the same tricks that I just told you about, but as if they were done under laboratory conditions, as if the psychologists who were investigating them had said, now we're going to do this, and it just, if you read them, you can't tell all of the things went on, and you can't tell that it only worked 1 in 7 times. And if you do anything and you just tell me the successes and you say to me, what are the odds of that, Mr. Wise Guy? Well, it's a miracle, right? You just tell me the successes. Unfortunately, a lot of science publication is that way too, but okay. What are some lessons that I got? Maybe you can get to. Ooh, try this. Here are some lessons from BD. Okay. So one persistent causer of coincidences is this idea of multiplicity. We saw it before. If you allow coincidence, within a day, or if you allow coincidence if you match in this or that. For BD, he had many different things that could count as a coincidence. For example, if the Queen of Hearts was supposed to come out and it was the Queen of Diamonds, he'd say, I don't want credit for that. I'm really having trouble seeing the suits. Okay, that's one of the issues. Subject cheating. Unfortunately, many, many times when I've gone to watch a performance of a psychic, there's some sleight of hand that goes on. There was a craze about 20 years ago about spoon bending. People were supposed to be able to bend spoons with their minds. And I once went to a spoon bending contest in England. A friend of mine said, "Oh, come along, I'm a judge on a spoon bending contest." Okay. And I'm watching these little kids, 7-year-old kids, and they're stroking their spoons and looking at them and stuff like that. And you think, this is idiotic. But all of a sudden, there's some spoon that's bent like that. You think, what happened? What I noticed is when a kid jumps up and says, "Look at mine," the other kids will pull their chair forward, or they'll do something, and they get it. So even innocent kids, I don't know if they're doing it on purpose or why they're doing it, but there's a tremendous amount of cheating. This bundle of sticks idea, that a lot of flawed arguments don't make for one good argument. It's a classical image, Roman image. The bundle of sticks, of course, if you take an arrow, you can easily break it. If you take 3 arrows, you can't break them. But if you have several broken arrows, it's still broken. If you wanted to hear this story or have references to what I just told you, I'm not just telling you about it, I wrote it down, and it's an article I wrote called Statistical Problems in ESP Research in Science a while back. Okay, the last thing I'm going to do is to try to bring things together, and I call it Towards a Rational Theory, and really it's just things I've learned. The first thing is something I haven't talked about at all, and that's hidden cause. And in fact, that's the main thing that we do when we're scientists. We look at data for surprising patterns that we didn't expect, and then we try to figure out what caused them. So, when Jocelyn Bell, physicist, was looking at her data, and she saw a blip with a certain period, and she went to her advisor who made fun of her and said, "Oh, that's just fluctuations in the electric current," but it was pulsars. It's what we do all the time, look at data and try to find unexpected patterns. And so of course there could be a hidden cause, and that is a tremendous causer of coincidences. An aspect of that that's very important is this question, is it true? So I'm out here telling stories, right? So I get told a lot of stories also. People will come up to, listen to this, what do you think about that? How true are the stories that people tell? That's an interesting question. How much do people lie? It's a lot. Okay, sorry, but it's a lot. So, somebody tells you a story. Did it happen to them? Did it happen last week? Did it happen to their sister 7 years ago? Did it happen the way they told it? Did they leave out pertinent details? I have thought about trying to do experiments like publishing a fake book review in the college newspaper and then asking people at a party, "Did you read that book?" I could be a really bad guest. But what I was surprised to find is it's very, very difficult to get useful answers to that question. It just, the data isn't there. Okay, multiple endpoints is again something that we talk about. If you don't specify what counts as a coincidence, the chance of something happening is huge. So you went on a trip and you met somebody that you went to high school with on the Great Wall at the Great Wall of China. Yes, but if you'd met them in the Frankfurt airport or in a coffee shop in Berlin or here, you would have been equally as surprised. So many, many different things surprise us, and if you don't take account of that, you'll pay. The cost of close is, how sharp is your coincidence, and if you relax that, it makes them much more likely. This is another very important one, which I haven't talked about, but I will now, and I call it the law of truly large numbers. Okay, the law of truly large numbers says if you have enough people involved, any damn thing is likely to happen. So, Littlewood, when he was writing about coincidences, well, something should count as a coincidence if it happens with chance bigger than, smaller, sorry, than 1 in a million. It should have chance 1 in a million. Well, at least in the US, there are 400 million people. So I should have 400 people every day, saying, hey, what are the odds of this, Mr. Wise Guy? And now, so if you do have 1 million people, the chance there are 400 million people, lots of 1 in a million coincidences will happen, and they are genuinely 1 in a million coincidences. And if you just pick out one and say, what are the odds of that? It's 1 in a million. But if you say, well, there's however many billion people there are on the planet, and a point is, when a coincidence happens, that gets told, and it gets reported and put in the newspaper, and so people yell out. People don't tell you about the coincidences that don't happen. And when they do, it's deadly. I have a friend, Brad Efron, who came up to me and said, yesterday was my birthday. And I said, oh, happy birthday, Brad. And he said, and I ordered a new Toyota. And I said, oh, and he said, and it didn't come. There's sort of numerator-only problems. I just tell you this, not that. Okay. As an example, the New York Times reported this number. A woman won the lottery twice, 1 week after another. And they said the chance of that happening is, 1 in a trillion. And that number is the right answer to a very funny question. If she bought 2 lottery tickets, one week, one the next week, what's the chance that she would win those 2 weeks in a row? That's 1 in a trillion. This woman bought 70 lottery tickets a week in multiple states, and she's only one person. There's lots of people buying lottery tickets, right? And if any one of them, and by the way, her win wasn't 1 week apart, it was 8 months apart, okay? If any one of them won the lottery twice, it gets in the newspapers, and that's our miracle, right? So we did the calculation, and we calculated that it was chance 1 in 30 that there was be another double lottery winner within a 4-month period in the U.S. And to be honest, we lost the bet. We bet the reporter that, but we lost the bet. But still, it's not a miracle. It's pretty likely. So those are all things to think about when somebody tells you an amazing story. And here's my last slide. And if I wanted to go into business, be a guru, I would start this way. I want to tell you about a new synchronicity. There's something beyond cause and beyond chance. Sounds great. It's this. Coincidences happen in the minds of an observer. None of us probably, very few of us are equipped to think about this, but the psychology of coincidences is much more potent than the mathematics, actually. And what are some examples? There's some study of that sort. So memory failure, that is, you just forget things that you saw. Let me see if I could give you an example. So, for example, I'm interested in magic tricks. As I wandered around, there was a picture of a guy flipping a coin that was on every street post. But if I wandered around and if there was a magic show being advertised, I would have noticed it. I'm not aware of noticing it, but we do that. We parse an awful lot of data subconsciously. And then if something matches, we call attention to it. There's a familiar example of it, and you can witness it the next time you're at the Congress. You're at a very crowded party. You can hardly hear the person you're talking to, but if somebody says your name across the room, what's that? This cocktail party phenomenon. So we monitor all kinds of things, and so selective attention is another real causer of coincidences. An interesting one that was demonstrated experimentally, Ruma Falk did this, an Israeli psychologist. She had people record their coincidences and say how surprising they were on a scale of 1 to 10. And people think their coincidences are much more surprising than other people's coincidences. So, makes sense. I mean, you know what went into yours, you don't know what went into the others, and etc. This is a subject, it hasn't been developed. There's one part of it which I'm sure is true, but I can't make scientific sense out of it, but I'm going to say it anyway. And that's hardwiring. You're not even supposed to say that out loud, I think. But so as we were developing, I'm picturing primitive man in the jungle, and you look over at the bush and there are some stripes, and maybe it's a tiger. And maybe you just better get out of there and not figure out the odds that it's a tiger. Okay? So we're hardwired to recognize structure and patterns in what should be a noisy background. And I think there's no question about that, although I don't know what hardwiring means. And given that our wiring system was developed, however many million years ago, and the number of inputs that we have is, much, much richer today, the fact that there are lots and lots of things that we see that surprise us, that we notice this and we notice that, and how could it have happened, seems even forced on us. If you wanted to read more about this subject, a lot of the stories I just told you were written down in Fred Marsteller's presidential address, and here's a reference to it, Methods for Studying Coincidences. And let me leave you with this. Fred Marsteller, who was, he calls the talk I've just given you "Nyeh talk." Yeah, it's not so surprising. I don't think about it that way. All of the calculations I did with the birthday problem come from the law of small numbers, the Poisson approximation. Jung's explanation, my explanation of Jung, comes from study of Poisson process. The thought that a handful of mathematical ideas could explain a world full of coincidences, that's as marvelous to me as the coincidences that happen. I hope I've given you a picture of the kinds of things that excite me, and thanks for coming.